So, you want to make your software faster, right? We all do. But how do you actually measure if one approach is better than another? And I'll give you a hint. It's not as simple as just pulling out a stopwatch. Let's really get into it. Here's the game plan for this explainer. First, we're going to see exactly why just timing your code is a pretty terrible idea. Then we'll need to create a level playing field, so we'll look at a universal computer model. From there, we'll learn the language of efficiency itself, big O notation. We'll use it to climb what I call the complexity ladder. And finally, we'll bring it all home and see what this all means in the real world. All right, picture this. You've come up with two different ways to solve the exact same problem. They both get the right answer, but the big question is, which one is actually better? This is something developers face every single day, and the answer, well, it's not always what you'd think. I mean, look at this. If you just time your two algorithms, the results are all over the map. On your super fast laptop, algorithm A looks like the clear winner. But then you run the same code on an old server, and whoops, now algorithm B is faster. And then there's the data. With a small amount, A wins, but feed them a massive data set, and B completely smokes it. It's a mess, right? And that right there, that total unpredictability, is exactly why speed isn't enough. We have to find a better way, a method to measure the true, inherent quality of an algorithm, no matter what machine it's on or how much data it's crunching. We need a standard. The dream really is to have a universal yardstick, something that lets us compare apples to apples, whether the code is in Python or Java, running on a supercomputer or your phone. We gotta level the playing field. So how on earth do we do that? Well, a long time ago, computer scientists came up with a pretty brilliant solution. They invented a theoretical computer, a universal model that everyone can use as a standard reference. And here it is. It's called the Random Access Machine, or RAM model. Now, hold on, don't confuse this with the memory sticks in your computer. This RAM is completely abstract. It's an imaginary, idealized computer that lets us analyze algorithms in a perfectly pure, controlled environment. And the way it works is actually pretty simple. On this theoretical machine, we just decide that every basic operation, adding numbers, assigning a variable, takes the exact same amount of time. We'll call it one time step. So to figure out how expensive an algorithm is, we just count up all the steps it takes to finish its job. Now, counting steps is a great idea in theory, but in practice, can you imagine counting billions or even trillions of individual operations? That's just not practical. There has to be a simpler, more elegant way to talk about performance. And there is. It's called big O notation. I mean, think about it for a second. Do we really care if an algorithm takes, say, 503 steps versus 512? Or are we more interested in the bigger question? What happens to the runtime when our data doubles or grows by a factor of 1,000,000? It's all about how it scales. And that is exactly what big O notation is for. It's the language we use to describe efficiency. Big O couldn't care less about the exact number of operations. Instead, it describes the growth rate. It gives us a high-level picture of how the work an algorithm has to do changes as the input size gets bigger and bigger. Now, with Big O in our toolkit, we can start sorting algorithms into different performance classes. I like to think of it as a ladder. The absolute best performing algorithms are on the bottom rungs, and as you climb higher, things get progressively slower and more expensive. And here are the usual suspects, the most common rungs on that ladder, ordered from best to worst. We've got amazing performers down at the bottom, like constant and logarithmic. Then we move up to the very respectable linear and linear arithmetic. But then we start getting into the danger zone, with quadratic and, at the very top, the terrifying exponential. So, O of 1, or constant time, is the absolute dream. It means your algorithm takes the same amount of time no matter if you give it 10 items or 10 billion. Right next to it is O of log n, or logarithmic, which is also fantastic. Think of searching a dictionary. You don't read every word. You keep splitting the problem in half. Then you have O of n, linear time, where the runtime grows in direct proportion to the input. Double the data, you double the time. It's very common and totally predictable. Now we're starting to climb into more costly territory, O of n squared, or quadratic complexity. This is where the number of operations explodes. It grows with the square of your input size. And if you've ever written a loop that runs inside another loop over the same data, well, you've probably written a quadratic algorithm. This is where performance can really start to hurt. Okay, this table right here, this is where it all clicks. This is where the theory gets real and honestly a little bit scary. Look, with just 10 items, who cares, right? The differences are tiny. But watch what happens when we get to 1,000,000 items. The linear algorithm is fine, but the quadratic one is already at 1,000,000,000,000 operations. 1,000,000,000,000. And the exponential one, forget about it. The number is literally too big to even write down. That is the power of complexity. So you might be thinking, okay, cool, math, but so what? Well, this isn't just some abstract exercise. Understanding this stuff has huge, tangible, real-world implications for any piece of software you ever build. This is the key. Big O analysis gives you a kind of superpower. It lets you predict the future. It allows you to know with a high degree of confidence how your code is going to behave under serious pressure with tons of data, not just the 10 little test items you tried on your laptop. And the consequences of choosing the wrong algorithm can be pretty severe. As one source puts it, even a fairly common ON squared algorithm, that nested loop we talked about, could easily run for hours or maybe even days before it finds an answer on a large dataset. And if you think that's bad, just look what happens when we take one more step up that ladder. With an O of n cubed algorithm, we're not talking about days anymore. We could be talking about years. This shows why picking the right algorithm isn't just a minor optimization. It is absolutely fundamental. At the end of the day, a more efficient algorithm isn't just about elegant code. It translates directly into saving real time, real computing resources, and real money. It's the difference between software that scales beautifully and software that crashes and burns. It's the absolute bedrock of professional software engineering. So, I'll leave you with this question. The next time you sit down to write some code, don't just ask yourself, does this work? Ask yourself, how does this scale? What is the true cost of the solution I'm about to build? The answer might just change the way you code. Hey, if you found this breakdown helpful, do us a favor and hit that like button, share it with a friend, and make sure you subscribe for more explainers just like this one. Thanks for watching.